In this video, we'll be talking about angular momentum. Now, what is angular momentum? Well, it's momentum for rotational objects. And this is one of my more, interesting topics of physics because it does really weird things. If you've seen videos of people sitting on a chair that can rotate, but the chair isn't rotating right now, and they're holding out a wheel vertically in front of them, and that wheel is spinning. Once they turn the wheel to the side, the person starts spinning on the chair as well, which is kind of weird. I'll have a video down in the description to show you what I'm talking about, but it's very interesting. And you've also seen ballerinas do spins, and when they close their hands together, they start spinning faster. Well, that's due to angular momentum. So let me show you first things first how to calculate angular momentum. It's actually the important thing. And keep in mind, angular momentum is a vector value. So angular momentum is calculated by moment of inertia times angular velocity. So how do you derive this equation? Well, lazy way to derive it is the formula for linear momentum is simply mass times velocity. Well, the mass equivalent in rotation is moment of inertia. And the velocity equivalent in rotation is just angular velocity. So all I did was just replace mass with moment of inertia and velocity with angular velocity. And using this, you can calculate the unit for angular momentum. So the unit for angular momentum is, well, if the unit for moment of inertia is kilogram meters per second, and the unit for angular velocity is radians per second, but radians isn't a real unit, so it's just 1 over seconds technically, then the unit for angular momentum is just kilogram meters squared over seconds. Well, this is one way to calculate angular momentum. Another way to calculate angular momentum is the cross product of a linear momentum from the distance vector, from the axis of rotation. So what do I mean by this? Well, if you have a spinning or a grindstone, let's say, you have an apple. Let's see, you have an apple that is traveling towards the grindstone. This apple is traveling towards the grindstone with some velocity. Well, therefore, if it has some velocity, well, this is our momentum. This is our linear momentum right here, represented by the blue arrow, and the apple right here is represented, or the r distance vector is represented by the blue arrow here. The distance vector is just r. Now, using a cross product, you can also calculate that using some determinant of a matrix. But you can also calculate cross products using magnitudes. So the magnitude of your momentum times the magnitude of your distance times the sine of the angle between the two vectors. Now, keep in mind, the angle between the two vectors must be tail to tail when the vectors are tail to tail. So the vectors need to be tail to tail. So always keep that in mind. And the angle theta is the shortest angle between these two vectors. Now, don't take this angle here because you'll get the problem wrong. Take the angle between the two vectors when they're tail to tail to use for your formula for this cross product. Now, on a quick side note, you don't want to take the larger angle like so. It's wrong. You usually want to take the shorter angle for your cross products. Now, how about the law of conservation of angular momentum? So the law of conservation of angular momentum. Well, this is where interesting stuff actually happens. So the angular momentum of the initial state of some system before some collision happens or for some interaction happens always equals some final state, or what we determine as the final state. So just like any conservation law, initial must equal final. So if you were to calculate the angular momentum of this apple using the cross product here, and once it collides with this, and once this apple collides with your spinning wheel, and it completely stops and sticks to it, the angular momentum of the now spinning wheel, if this apple actually hits this wheel, should be equal to the angular momentum of the apple before any collision happens. Now, we're going to do some problems to help you understand what I mean by this. Now, for this problem, I specifically chose it because I thought it was actually pretty good explaining a concept of angular momentum that you might be a little confused about right now. You might be thinking, if the cross product of some angular momentum depends on distance, does that mean that your angular momentum changes throughout distance? Well, that actually does not matter. I'll explain what I mean by that right now. So let's actually do this problem. We know that the mass of the airplane is 40,000 kilos and has an altitude of 10 kilometers above some ground. So let's draw the airplane. I don't think this airplane will fly if it took off, but this is our airplane and is 10 kilometers above the ground. So 10 kilometers with a constant speed of 250 meters per second relative to the Earth. So it's just traveling horizontally, stay in the problem, at a speed of 250 meters per second. What is the magnitude of the airplane's angular momentum relative to the ground observer? So relative to a ground observer directly below the plane. So if the person is right below the plane, this is what they will look like. Well, if the person is right below the plane and we're trying to take the magnitude of the angular momentum relative to a ground observer, that means that our ground observer is our axis of rotation. So this is our distance vector for your cross product formula. Sine of theta. And for this formula, you need a momentum of the plane. So we can calculate the momentum of the plane, or linear momentum, by just using mass times velocity. Well, if you multiply 40,000 times 250, which is its velocity, you should get a momentum 10 to the power of 7 kilogram meters per second. So this is your momentum of your plane, linear momentum more specifically, and we can save it because that's important. Okay, well, the magnitude of r is just 10 kilometers. So we have your 10 to the power of 7 for the momentum, and we have your distance from the axis of rotation in the plane, and the distance is 10 to the power of 4 meters. Now all we need is the sine of the angle between them. Well, since the momentum is traveling straight horizontally, we can draw another horizontal vector, and this vector represents your momentum. And due to the fact that this distance vector is straight up and this momentum vector is straight to the right, the angle between them is 90 degrees. So if we multiply 10 to the power of 7 times 10 to the power of 4 times sine of 90, sine of 90 is just equal to 1. So 10 to the power of 7 times 10 to the power of 4 is equal to 10 to the power of 11 kilogram meters squared over seconds. So this is our answer for part A. Now how about for part B? For part B, we need to solve the angular momentum as the airplane flies along a constant altitude. So what does this mean? Well, let's draw the airplane again. And we're trying to see if the angular momentum changes as the airplane flies along. So as the airplane maybe is flying in, let's draw it ahead actually. The airplane's maybe flying here. Okay, it's sideways. Flying like this. And its velocity is still going in this direction. We can assume that the airplane still flies at a constant speed of 250 meters per second, as it says in the problem. So the momentum, and if the mass of the airplane doesn't change, that means the momentum is still 10 to the power of 7 kilogram meters over seconds. Well, if the airplane keeps flying forward, that means your distance vector is different. So your distance vector is now kind of slanted. Let me tell you the reason why this doesn't matter. Well, although this distance vector is slanted, due to the some property of sine, we know that this doesn't do anything to your angular momentum. So if this is the formula for your angular momentum, then r of sine does something weird. First, let's put the vectors tail to tail. So the vectors are now tail to tail. And this is your momentum vector. Well, if you multiply the magnitude of your distance, which is sort of the hypotenuse in a triangle, so if you multiply the magnitude of your distance by the sine of theta, the angle between the two vectors, which coincidentally is an angle on this triangle. Well, not coincidentally in this case, but if we multiply r times the sine of theta, we will get the magnitude of the y component of this r, or this distance vector. And the y component of this distance vector, well, if it's the y component and the airplane is determined r to be 10 kilometers off the floor, that means the y component of your distance vector is just 10 kilometers. So if your momentum is the same, so this is still 10 to the power of 7, and r times sine of theta is still 10 to the power of 4 meters, 10 kilometers, then if you multiply these two together, they'll still equal 10 to the power of 11 kilogram meters squared over seconds. So your angular momentum still stays the same due to the property of sine of theta. So this problem is one of the funner ones, and it kind of describes what I mean by a figure skater that there's a spin, and when they bring their arms in, they spin faster. So this is a pretty good way how to do this math in a super simple way. Now in reality, you're not gonna have calculations this simple, but let's start off with the problem. So there's a person sitting on a spinning stool with their arms straight out, then they pull their arms in against their body. You could treat the body as a uniform cylinder with mass 75 kilos, and uniform cylinder already tells us we're calculating moment of inertia. So we're going to use your moment of inertia formula for your angular momentum. Now, the radius of this body is 30 centimeters, which is also 0.3 meters. So let's write that down. And each arm has point masses. Okay. So this problem is already indicating that we're going to use moment of inertia. So let's write down m r squared divided by 2. And this is the formula for moment of inertia of a cylinder. So cylinder. And for point masses, the arms in this case, that have a mass, let's write big M. Let's differentiate those two. Big M r squared has a mass of 5 kilos. And the arm start a distance of 3 times r. R is 0.3. So in this case, the arms are 0.9 meters away from the center of the body and end up at a distance of r. Therefore, they bring their arms in. Find the angular velocity of the person after they bring their arms in. If their initial... What the... Okay. No, I'm sorry. Something just honked outside my window. Okay, but find the angular velocity of the person after they bring their arms in if their initial angular velocity was 4 radians per second. So their angular velocity before they brought their arms in was 4 radians per second. Well, in order to do this, we need to calculate the initial moment of inertia. Let's go ahead and calculate that. Let's treat the initial state like part A. So part A, we're going to calculate your moment of inertia. So let's calculate your moment of inertia, mr squared over 2. So calculate the moment of inertia of the body, 75 kilos times 0.3 meters squared divided by 2. So the moment of inertia of this person's body is 3.375 kilogram meters squared. Okay, let's calculate the moment of inertia of the person's arms. So if you calculate the moment of inertia of the arms, it's simply 5 kilos times 0.9 squared and times 2, because this person has 2 arms, hopefully. So if we multiply this by 2, then you should get a moment of inertia of the arms as 8.1 kilogram meters squared. So all we need to do is add these two together. So 8.1 plus 3.375 is equal to 11.475. So this is your initial moment of inertia before the person brings their arms in. and the initial angular velocity is 4 radians per second. So all we need to do is multiply moment of inertia times angular velocity. So 11.475 times, let's write the units, times 4 radians per second. And your initial angular momentum is just 45.9 kilogram. I need more space. Kilogram meters squared over seconds. So this is your initial angular momentum. We're going to use this for a calculation of the second case. So the second case is when the person brings their arms in. We'll treat that as part B. Now, what do we do here? Well, we know that the law of conservation of angular momentum states that the initial angular momentum should be equal to the final. So the initial state right here, 45.9 kilogram meters per second, should be the same even after the person brings their arms in. So what do we do here? Well, we have your final angular momentum, and we're trying to solve for the angular velocity. So if you solve for the angular velocity using your formula here, then you get angular momentum divided by moment of inertia. So in this case, we have 45.9 as your angular momentum, but we need to calculate moment of inertia. We can actually do that. So the moment of inertia of the body stays the same. It's still 3.375. But the arms are now inwards. So let's calculate the moment of inertia of the arms now. So mr squared is the moment of inertia, formula for point masses. And if you multiply mass of the arms, which were 5 kilos, times the radius, now they end up at a distance of r, and r is just 0.3 meters squared. We can multiply this by 2 as well to get the moment of inertia of both the arms. So we can have 5 times 0.3 squared times 2, and that equals 0.9. So 0.9 kilogram meters squared. So we just need to add these two together, and we can get the final moment of inertia after the person brings their arms in, which is 3.03, oops, wrong, I did that wrong, hold up, plus 4.275 kilogram meters squared. So this is the moment of inertia after the person brings their arms in. So let's use this formula here. So we have a angular momentum of 45.9 divided by 4.275, which is your moment of inertia. So if you divide 45.9 divided by your moment of inertia, you should get an angular velocity of 10.74 radians per second. So as you can tell here, your person's initial angular velocity was 4 radians per second, but once they brought their arms in, now their angular velocity is near it's actually over 2.5 times more. 2.5 times more. Therefore, this person is spinning 2.5 times more faster. So this is kind of the analogy of the figure skater that's spinning. When they bring their arms in, their angular momentum stays the same, but their moment of inertia changes. Therefore, they will spin faster. So if the moment of inertia decreases, then the person spins faster. If the moment of inertia increases, then the person will spin slower. So, as always, I need to mention OpenStax. It's a free online textbook, and I get my problems from there. Link will be down in the description if you want some problems yourself. But if this video helped, consider hitting the subscribe button. I would greatly appreciate it. But, as always, if you have any questions, put it down in the comment section.